All right, we are going to be going over the fourth problem on the harmonic motion problem set. It's going to be the fox population problem. So let's go ahead and read this one. I am going to go through this one a little differently. I'm not going to create a really accurate graph like I have in some of the other ones. I'm just going to kind of use kind of a sketch of the graph to help me write the equation. So here we go. Naturalists find the populations of some kind of predatory animals vary periodically. That's another way to talk about sinusoidal variation. Assume that the population of foxes in a certain forest varies sinusoidally with time. Records started being kept when t equals 0 years. A minimum number, 200 foxes, occurred at t equals 2.9 years. The next maximum, 800 foxes, occurred at 5.1 years. Okay. We're going between 200 and 800. So I'm just going to sketch this out. 200, 800. Between that in the middle is 500. So our midline is 500. At 2.9 years, we had a minimum. Yeah, minimum. Okay. And at 5.1 years, we had a maximum. So this difference right here between 2.9 and 5.1, that is 2.2 years, right? 2.2 years. So the difference between the maximum here and then the next minimum is going to, again, be 2.2 years. So adding that on there, we get 7.3. So 7.3. That will be when we hit another max or another minimum. I'm kind of going through this without spending a lot of time talking about it here. I'm kind of using a cosine curve. This is actually a reflected cosine curve. I kind of have enough information right now for me to sort of kind of figure things out at this point. I could sketch in my graph and work on it. Man, that's not great, but that's okay. So let's go ahead and talk about the different aspects. So here is our amplitude. It's going to be 300. Difference in population from the midline to the maximum, midline to the minimum. So our amplitude is 300. Actually, it's going to be a negative because we also are dealing with a reflected graph here. Our period is actually 4.4 years, and hopefully you can see that it was 2.2 from a minimum to a max, and then 2.2 again, so that's a total of 4.4. So our b value is 2 pi over 4.4. Simplify that, I don't know, however you want. You could leave it in this way. I'm going to reduce it by a factor of 2. So I'm going to use a b of pi over 2.2. Yeah, both of these are fine. Doesn't really matter. C value, where did we start? We shifted to the right 2.9, so that's my C value. And D, my midline is at 500, vertical shift of 500. So I have everything here that I need to write the equation, so I'll go ahead and do that. Negative 300. Cosine, it's reflected cosine, so we have a negative there. We have pi over 2.2 times x minus 2.9 plus 500. So there we go. That's the equation that models this situation. Again, I didn't make a super detailed graph, just kind of threw some numbers on there and approximated the scaling. That just doesn't matter. I'm just using it to kind of help me figure things out for my equation. Let's go ahead and move forward and try to answer some questions about this particular problem. So here's the equation we just came up with, same one that we had. So we can use the equation to predict the population at any given time. We'll just replace the time with our x variable in this case. Again, pretty simple. We could do it on a graph. We could use a calculator to do it and just calculate this. Again, just replacing the x with a 7. And forgot a parenthesis there. I'm going to go ahead and do that real quick. Negative 300 cosine. Again, remember to have your calculator in radians. If it's not in radians, you're going to run into difficulties here. You're going to get the wrong answer. Okay, so I got 227.11. It's worthwhile to just sort of glance back at our graph. 227.1. Let's go ahead and glance back at that graph that we just had. So we were at 7. And so 7 would be, right in this region. So being just above 200, that makes sense. Yeah. So it's worthwhile to go back to your graph and make sure that your answer did make sense, that you didn't make some sort of an error there. We could also graph it on Desmos and find that answer that way too. But it's nice to check and confirm that you're getting the same answer that you had before. All right. Okay. Obviously, we can't have 0.1 foxes, so you could get off that decimal and just go to a whole number. But anyway. All right, foxes are declared an endangered species when their population drops below 300. So far, we haven't actually solved this algebraically before, but I want to go ahead and try it right now and see what happens with our solution. And then we'll check that solution on a graph. So the population is y, so let's go ahead and replace our population with 300. And I'll go ahead and write out this equation now, and I'll talk about how we need to solve it. All right, plus 500. Okay, so we have an equation. One thing that's really important that people kind of forget is kind of all of this stuff is sort of locked away. All these things in the parentheses are all part of what's being inside the cosine function. So I'm going to need to get rid of this plus 500, and I'm going to need to get rid of this multiplication by negative 300 before I can really touch that cosine at all. Let's go ahead and do this, subtracting 500. We get negative 200 equals negative 300 cosine. Okay, and again, we have to divide this multiplier, this a value in front, so I have to divide by negative 300. And we get, that reduces simply to 2/3. Negative divided by negative is positive. 200, 300 is 2/3. And here is where we actually need to start messing with getting rid of this cosine function. So we have to know what to do now. What do we do at this point? We got to be able to cancel out this cosine. So all of our other operations have inverses to them. They have opposites, right? To get rid of addition, we use subtraction. To get rid of multiplication here, right? These are multiplied, we divide it. So everything has an inverse. Cosine has an inverse. It's called cosine inverse. So we just simply take cosine inverse of both sides of this function. I'm going to write this out like this. So cosine inverse of 2/3. That's that side. And the cosine inverse will actually just cancel out cosine. They're opposites, just like adding and subtracting. Cosine and cosine inverse are opposites. They end up canceling. So we end up with pi over 2.2 times x minus 2.9. Yep. So now we're kind of at the point here where we want to solve. I could use a calculator to get a decimal here, but I'm going to refrain from doing that until the end, until I'm kind of at the point there. So I want to get rid of this multiplier. So I'm going to multiply both sides by the reciprocal of that. So I get 2.2 over pi. So again, I'm multiplying by that by 2.2 over pi. It cancels on this side and it gets multiplied on this side. So I get 2.2 over pi times the cosine inverse of 2/3 equals x minus 2.9. And then I just have to add 2.9. I'm going to take this whole mess here and I'm going to calculate that. So I'm going to use my calculator now to get a decimal approximation. So 2.2 over pi times cosine inverse of 2/3. Okay, I got this. And now I'm going to add 2.9 to that. So plus 2.9. Okay, so there we go. 3.48, 3.5. I'm just going to go 3.5. Let's do 3.49 is approximately x. So here's an approximation, 2 decimal places. So that's 3.49 years. And let's check the solution by looking at the graph. That's what I'm going to do. I'm going to check the solution by looking at the graph. So I got to type in this equation here. pi over 2.2 times x minus 2.9 plus 500. And we got to mess with the scaling quite a bit. X-axis, let's just count by ones. I don't know what our x-axis really needs to do, but the y-axis needs to be adjusted quite a bit. Let's just go from 0 to 1,000 and count by 100. Okay, so here we go. Here's our graph. We see it oscillating between 200 and 800. You know, mess with your scaling until it seems appropriate to you. We are looking for when the population drops below 300. Pay attention carefully to that language, right? So let's put a horizontal line at 300 and just see the different places. So here is where they started taking data, right there, year 0, time 0. And then it went up to there, down. Okay. Here is the first time that it dropped below 300. This is the answer we were looking for. We had an answer of, I can't remember, it was 3.49, right? But right here, this is where the population is above it, and now it's going and it drops below 300. Right here at this point, this is when it hits that and it's going below. What did we get then? What were we getting? Didn't mean to do that. What were we getting here? We found this number. Certainly the population is equal to 300 here. So our solution was valid, it was fine. It just wasn't the answer. So this is why we have to be careful using that algebraic approach. It's totally fine for us to solve and get this, but we do need to make sure that this specifically answered the question that we were looking for. And in our case, it did not. This was not the solution. The real solution here was t equals 2.311, whatever. So you got to be careful. You know, algebraic methods are totally fine, but you do need to look back and make sure that it does solve the problem. I mean, it did find us a value where the population was 300. It just didn't find the right one. You know, there's a lot of them. You can keep seeing them. There's an infinite number of them as we keep going this way. All right, let's go ahead and go back here, and we're going to do kind of a last problem. So this one's kind of a modification or variation of the 5th problem on the worksheet. It's called the bouncing spring problem. So in this case, we're going to start off with this equation. And we're going to kind of do the same thing. We're going to see how the equation works for us. So this is the equation of the motion of a spring. You can see the picture of here. It's kind of suspended. There's a weight hanging from it, and it's bouncing up and down. And its height above the table or ground, I guess floor in this case, is varying sinusoidally. It's going up and down, closer and farther over time. And so here's the equation of its motion. So its midline value is 50 and its amplitude is 10. So it's 50 at its equilibrium or midline, and it's going 10 above that. So it's going up to 60 centimeters above and down to 40. And you can see that in the picture here. Here's the question we're trying to answer. We're trying to use this equation to help us answer this question right here. At what time does the spring reach its minimum height of 40 centimeters for the 2nd time? I'm going to go ahead and solve this first. I'm going to use the algebraic method. So the height is y, and the t is the time. So we're going to substitute 40 centimeters for y, and we're going to try the algebraic method here. We're going to see how this works for us. And then we will compare that answer to our graph. All right, so I'm going to subtract 50 on both sides, minus 50. And to save time, I'm also going to divide by 10 after that to get rid of that 10. Divide this by 10. So we end up with negative 10 over 10, which is negative 1. All right, so that helps us out a little bit. 2 pi over 3 t minus 11.55. I just didn't want to have to write this out twice, so I did both of those things kind of in sequence. I subtracted 50 which gave us this -10, and then I divided by 10, just to save a little writing. So now we need to get rid of sine. We got to do sine inverse, so we're going to get rid of that. We'll have sine inverse of -1. Sine inverse of -1 is actually a nice value because on the unit circle, there's only one coordinate, one place that has a sine value of -1. That's all the way down at the bottom of our unit circle. So that would be pi over 2, -pi over 2, or 3 pi over 2, however you do that. So I'm actually gonna calculate this. I'm gonna do shift sine -1. Let's keep this exact for a while. So let's leave that there. We got sine inverse -1 equals 2 pi over 3 times t minus 11.5. Okay, to get t all by itself, we got to multiply by the reciprocal here. So that's 3 over 2 pi times sine inverse -1. And then I'm going to add 11.5. Get rid of that. So plus 11.5. So now I can perform all my calculations here. I kept it exact until this point. So let's go ahead and do that. Let's do 3 over 2 pi times sine inverse of -1. Okay. And then I'm going to add 11.5. Okay. So here's my calculations. There we go. So I get 10.75. 10.75. So that is my answer that I'm going to be working with. And that was actually exact. So no rounding was even necessary there. So 10.75. I'm kind of curious, that answer is suspicious to me. We're saying that the spring is gonna, or the weight is gonna reach its minimum height on the second time. So it's gonna go down, up, down. And that's gonna take 10.75 seconds. This seems slow. Feels like it would bounce a little faster than this. So let's go ahead and examine this graph. Let's do that. So let's go to my desktop here. We gotta adjust some things. And let's put in our new equation. So it's 10 sine 2 pi over 3 x minus 11.55 close parentheses plus 50. I'm going to double check that equation. Yep, looks good. Okay. And we know our graph is a little bit off here. We only want to go 0. Let's just go like 0 to 80. Okay. Let's get even closer. Let's go like 30 to 80. We'll step by, I don't know, 5s. Okay. Don't like all this stuff here. I didn't realize that was still there from the previous problem. Okay, so let's go ahead and examine this. So we're looking for the second time that it reaches its minimum height. So again, let's go back to the graph. So here's where we're starting. So we don't care about anything over there. Starting here, it goes up to its maximum, down to its minimum. So that's the first time. Up to its maximum, down to its minimum. So here's the second time. So the answer we got of 10.75, we got t equals 10.75. That's not the answer. The answer that we really needed for this problem was 4.8 seconds. That's when it reached for its second time. So solving algebraically has its limitations, and let's talk about why. It has to do with this phase shift. See this phase shift right here? This tells me that this graph, it's a sine graph, shifted over 11.5 seconds. So 11.5 seconds. So talking right here, that's about 11.5, yeah. So we are looking at this section. When we use this equation, we are only looking at this section of the graph. And of course, the number that we found was around this region, right? And actually, the number we found was right here. That's because of the way that inverse sine works. So it's a bit of a mistake. That phase shift of 11.5 seconds is still valid. when you do inverse sine, it looks actually in this region. So here is our sine curve, and it's looking for a solution in between those particular numbers right there and right there, 10.75. So it found a solution, but it only found a solution in a set window. It didn't necessarily find the solution we were looking for. So, you know, we could have used the period of this thing to shift it back until we found which one was the first one and then kind of gone there. But the graph is going to be the way to go with these problems. All right. Good luck on the 3.2 harmonic motion check. I will see you guys later.